as we keep going with these historical climate changes and come towards global warming or 20th century warming, which we will call modern climate change, just to distinguish from the historical climate change. So we will start looking at the forcings, and we will see that as we go more and more to explaining why things have changed, we will expand our display to many fields: ocean, atmosphere, land, ice, ecosystems, and so on. Then the forcing and the feedbacks become more and more important. I already mentioned several times the sunspots. We already said that minimum sunspots correspond to increased radiation because of the so-called plage that we will revisit again and again. Those are buried in the C14 information because the production of C14 changes. And if you remember, we compare C14 and tree rings and so on, sense of the variability in C14 production. And we said the end of the medieval warm period and the beginning of the Little Ice Age is recorded in many quantities, like the Icelandic sea ice around Iceland. And we stopped here showing that reconstructing past land use change. Generally, the term is land use, land change. You will see this a lot in papers and satellite data and so on. So with satellite data, we can do it much more reliably, but when we go back to the past, often we rely on models. So this one relies on population impact, and this one relies on more historical evidences and combine them. And you can see the differences are not small in terms of forested fraction. Here it's almost 100%, but here it is saying that's down to about 20 or 30%. So that can make a massive difference. We can continue to build a story about what historical climate change is telling us coming out of the last glacial maximum, and where we think we could be headed if human impact was not so significant. So the models can again be used to see if the solar forcing and volcanic forcing were prescribed as observed in nature, and the human impacts were taken out in terms of the land use change, increased greenhouse gases. What would be the climate? So this is essentially showing that if we do not increase the carbon dioxide and methane concentrations and keep them at, let's say, pre-industrial level, then we would be kind of increasing the glaciation over Earth in general, and we would continue the cooling that started 50 million years ago, the recovery from the last ice age or deglaciation, and then heading back towards slowly the next glaciation. But that's not what is happening. So you start evidences of what is happening. So here we are looking at an ice cap from the Andes showing the delta O18 parts per mil or parts per thousand and the related dust amounts. Obviously, when the delta O18 is decreasing, it is getting warmer and the dust is decreasing. But you can see that as we come towards the post-industrial timescales, out of the Little Ice Age, where the delta O18 was concentrated or enriched, which means temperatures were colder, and the dust correspond, because usually we expect that when it is colder, dust increases, but because of conversion to agriculture, deforestation, etc., or maybe for some other reasons, the dust is not corresponding, and we are increasing the warming, so the ice melting or the enrichment of delta O18 is reduced. So you can see that more clearly here. So coming out of the last glacial maximum, this is the depth of the core now, not the time, but time is here on this side. So since the 1960s, you can see that the delta O18 has been varying on multi-year timescales. We are used to looking at orbital timescales and what we called millennial timescales. Now we are looking at multi-year timescales. Andes is in the South American western side, very close to the cold tongue or the cold waters off of the coast in the Pacific. So we expect that as El Nino comes and goes, it's going to have some impact on snowfall and ice and snow growth on the Andes. But there is a trend. If you begin to see, the melting had already started, and this is obvious in many places. So this is looking at the Dundee ice cap, and going from the beginning of the modern era or the common eras from zero. For the first time in this 2000-year period, the delta O18 has remained very high. So this is a scale you have to be, again, you have to get used to the scales of delta O18. When it's enriched, it is reduced in, so it is depleted. That means as it begins to get more O18, that means you are melting ice and reducing evaporation and so on and so forth. So it has high for 50-year period. That has never happened in the last 2000 years. So you are now beginning to get beyond natural variability and millennial timescales and coming out of the natural variability and emerging as a signal that points to human activities. This is what we will keep on doing. What are the natural variability ranges, and modern changes beginning to go beyond what we expect in terms of natural variability. So that in the lower latitudes, Tibet is in lower latitudes than Greenland, for example. So you try to put together multiple proxies. Here is Tibet, similar behavior in Greenland. We saw Peru has similar signature, but Antarctica is a bit confused. So it is worth looking at why Antarctica would be different, could be different, and we have to then go back to our ocean circulation, especially around the Southern Ocean. So we looked at the trade winds in the tropics and mid-latitude westerlies, polar easterlies, and so on. Those generate these eastward and westward currents, and they generate these circulations called subtropical gyres. And we said that on the western side, warm waters are carried to higher latitudes by the Gulf Stream in this case, Kuroshio in this case. Kuroshio, just for a quick digression, means black current in Japanese. Because this warm current is not productive, they doesn't have fish, they call it the black current. We know the Japanese love their fish. So this warm water that is being brought up here warms the atmosphere. Warm atmosphere can hold more moisture, so increases evaporation, and that's what drives deep water formation in the Jin seas or the Greenland, Iceland, Norwegian seas up here. And I already mentioned the Bering Strait, fresh water coming in here makes this colder. So you can see it's actually colder than here, but it's also fresher. So when you evaporate and increase salt, it's the combination of salt and temperature that gives you heavier density. So here, even though it's quite windy, the water is so fresh that the evaporation does not produce deep waters in the current setting. So those are the kind of ocean currents. Of course, the Indian Ocean currents reverse direction because of the monsoonal circulation reversing direction from the summer to winter months. And the other point I kind of mentioned but didn't emphasize enough maybe is that when you have boundaries like this, the winds that are trying to put energy into the ocean are limited by how much energy they can put into the ocean, because they eventually hit the other boundary. Whether they are blowing this way or this way, they start putting energy and they block by the coast on the other side. So the amount of energy that can go into is only about 2 to 5%. So all the waves you see at the beaches, in fact, integration of all the energy that's being put in. So you can imagine that since this is a bigger ocean, more energy is going into the ocean. So actually the waves and the surf will be stronger on this side. So if you're a surfer, you wouldn't go on this side because the winds coming off of the land have not put much energy in here in these latitudes where the winds are going this way and winds are going this way. So you will get more surf maybe on this side, but it will be less than on this side. It will be very less here compared to here, and so on. Why am I saying that? Because if you remember the Southern Ocean, it is completely like a channel. So the winds can keep on putting energy into this part of the world ocean. So in fact, the winds churn the ocean so much in the Southern Ocean that winds go all the way to the bottom and they start to drag on the bottom. That's what limits the amount of energy that can go in, because the friction with the bottom then begins how much more energy can go into the ocean. So that's one important thing, because that tends to isolate Antarctica. From the time that the Drake Passage opened, this kind of isolation is what allowed the glaciers to grow on Antarctica. The other piece we need to connect here to understand the difference between the northern glaciers and northern ocean circulation and Antarctica, general northern hemisphere glaciers and Antarctica, is to go back to our thermohaline circulation. This looks complicated, but if you stare at it for a few seconds, you will realize that it is just showing the three oceans, Indian, Atlantic and Pacific Oceans, with Antarctica in the middle. And we said there is deep water forming, North Atlantic deep water forming in the Jin seas, Greenland, Iceland, Norwegian seas. That water sinks pretty deep to the bottom, and then it's lighter, so it begins to go up as it goes south in the Atlantic Ocean, because in the Antarctic you are forming the heaviest water called Antarctic bottom water. So the Antarctic bottom water is actually the heaviest water of all. So you can see that there are many water masses being formed. So the classical oceanographers will go in ships, collect water samples, and they will figure out where the waters are coming from and getting mixed in those regions. So the Indian Ocean and the Pacific Ocean get these waters, and they are coming into the ocean and becoming surface waters and through the overturning circulation to the North Atlantic. So the Indian Ocean is obviously has much shorter extent because it's closed to the north because of the continents. So this time scale will be much faster than this time scale. So the waters here will be the oldest waters, and we will show later on. You can use C14 dating to see the age of these different waters. The other important thing that's for the Indian Ocean and Indian monsoon is that the Antarctic Ocean, which can keep on circulating, can take the global warming heat and mix it down pretty fast, faster than the other oceans. So Atlantic can mix it down, but only where the deep water is sinking. But the Antarctic can do it all around, and that water can come into the Indian Ocean and has to become surface water and come back out. And so you can see that some of the pathways back, which means the warming in the Southern Ocean penetrates and that reaches the Indian Ocean pretty fast. So the Indian Ocean warming is directly affected by this kind of local thermohaline circulation. So all these things make Antarctica much more different than the northern hemisphere. So you can now see the complicated currents. The famous polar current is here, which is kind of between the subtropical and the polar front, and the polar current is going here. There are different direction of currents in the Ross Sea gyre, Weddell Sea gyre, and so on. And here are the oceans, the Pacific, Atlantic and Indian Oceans. And to put together this idea of circulation, isolation, along with the warming of the ocean, you will begin to look at cartoons like this. This looks again quite complicated. So here is Antarctic glaciers growing and glaciers flowing, and as I said, the glaciers coming down the mountains always extend onto the ocean and form large shelf ice. It's basically glacier that has flown onto the ocean, and it's moving with the waves up and down, which makes it very vulnerable to be broken off from the main glacier with which it was attached, from which it formed. That can create problems of how the grounding line of the glacier continent can be affected. We looked at this a little bit when we are talking about millennial timescale variability. We said the glacier can push the continent down, allow the ocean to come in and push the glacier back. So similar things are happening here. So the water is going under the shelf ice, releasing heat or breaking it off, and then inundating further and beginning to melt the glacier and sometimes move the glacier grounding line back and so on. But life is never that simple, right? So imagine now what happens if the ocean is warming. With global warming, the ocean is warming. We will see again and again this point. We have lots of data to show this. If the ocean warms, the simple rule is the atmosphere above always warms. What happens to the atmosphere if it warms? So you will increase the heat loss from the ocean, which means evaporation, and heat gain by the atmosphere, so the condensation, which means you can actually increase precipitation on the glacier. So on the one hand, you are melting and breaking off, carving the icebergs. On the other hand, you are increasing precipitation. So the warming and cooling, I will show later on another diagram, on the Antarctic is quite complicated. So unlike the Greenland, so these are obviously warming and melting, whereas you can see here that Antarctica has had hiccups. It has had growth and it has had melting, but this is more like the little ice age, and this was coming out of the medieval period. And in the 20th century, it's still trying to decide what it wants to do, because overall depends on where you are on this complex terrain with mountains and oceans and so on, to see what the net result will be. So all the data we have, we will come back to look at the glacier changes later on. It will show that there are some places where glaciers are growing and there are some places where glaciers are melting over the Antarctic. What is happening? Poster child for global warming. The sea ice is melting at very rapid rates, and it's being watched very carefully because it's surrounded by so many countries. Each country wants to have a piece of it, as I said, because of past photosynthesis. Potentially there is a lot of hydrocarbons, energy, water, petroleum, gas, and so on. To have put a flag there and claim some region, but the evidence that the Arctic ice is melting is obviously growing. You can look at the tree rings from Asia and Arctic, and you can estimate temperature changes. This is coming basically from the more recent few centuries. You can see that again coming, the little ice age had some cooling and warming, and we have basically since the Industrial Revolution been warming these high latitude regions or high altitude regions. This is the Mongolian tree ring index, quite a bit of warming, 1.5 degrees or more, and the Arctic. So again, ice albedo feedback is going to be critical in the Arctic, as more energy is going to be absorbed into the ocean, more heating, more melting, and so on and so forth. Okay, very important region. We didn't say exactly how tree rings works. This is just a quick introduction. There will be a module. So basically people go and drill a small piece of the tree trunk. It could be alive or it could be dead. If it is alive, you can start counting the rings from outside to inside, and the number of rings they put down basically rings every year. So you can count how many years the tree has been growing, and the differences in the ring width record temperatures, droughts, and so on. So they calibrate and find a way to interpret what the tree ring is saying in terms of climate variability, where it is. So that's the simple idea of tree ring. If it is a dead tree, then often you use C14, figure out when this died, and then see how many years it lived in that period and how the climate changed during that period. So all coral tree rings or corals can be dead and fossilized, but there is a way to date them and see how much period they lived when they lived and what kind of climate information is locked in. So they don't necessarily have to be alive. So we'll keep coming to El Nino in many ways. We are just now adding various evidences, so you can see that if it looks disjointed, then don't worry, because all we are doing is looking at climate change evidences from the more recent period, what we call historic period, using various proxies. But as far as forcing goes, we have to constantly monitor what is natural forcing like volcanoes and sunspots, but also what El Nino is doing. So, these so-called internal variabilities climate, and we'll learn a little bit more about El Nino in a minute. So, the corals in the East Pacific record a oxygen 18 signal associated with El Nino. So, this is an El Nino, El Nino, El Nino, and so on. So, each El Nino changes the sea surface temperature, changes the evaporation, and the corals that surface in that water immediately begin to record that change in temperature and evaporation. So, that can be used to infer water temperature. So, obviously, in these periods we had water temperature information. So, they can be used together to calibrate and so on. And you can then reconstruct longer term coral based temperature reconstruction. So, this is sea surface temperature anomalies with respect to the period from 1961 to 1990. Usually what happens is when you measure temperature, you can measure absolute, but when you go back and reconstruct delta O18, it just gives you change in temperature, and you are comparing delta O18 to a standard sample, which means the anomaly surface temperature you infer from it will also be with respect to the standard sample during which the SSTs were recorded. So, you can see that going back to 1600s, we are essentially in the Little Ice Age. So, I am saying two things. We are talking about East Pacific, which is recording El Nino and La Nina signal. We didn't say much about La Nina. We have been saying El Nino, El Nino. We'll see in a minute that the opposite phase of El Nino is I will explain in a minute. So, there is a cooling related to the Little Ice Age, but within that you have El Ninos happening, right. So, as we come past the Industrial Revolution out of the Little Ice Age, you can see that there is a fairly rapid warming in the Pacific where these corals have been collected, and this also includes some Indian Ocean corals. Okay. This is how you begin to say whether we are warming in the recent period and whether that is going beyond natural variability. So, since we are here, I might as well say a little bit more about El Nino. So, as I said, in this section on historical climate change and modern climate change, I will add the details of the physics, the chemistry and the biology that we need to understand. So, we didn't do much of that when we did tectonic, orbital. We added a little bit of carbon chemistry to look at C14, delta O18, etc. But to understand the feedbacks better, especially at El Nino time scale and global warming time scale, we need to begin things like the carbon cycle and how the circulation affects the ocean production and so on. We have talked about upwelling and production, but we need to do a bit more. Is one of these critical modes of variability. It's a natural mode in the sense that it is not related to radiation changes from the sun or volcanic forcing. There is some argument that volcanoes can produce an El Nino, but El Ninos happen many times every 2 to 7 years, not forced by volcanoes. So, it is a natural mode of variability, has a time scale of 2 to 7 years, which is not related to any particular forcing, but just the redistribution of heat within the ocean. Where does the heat come from? Basically, you remember we have the trade winds which are pushing the water away from the coast as well as from the equator. So, if you want to push water near the equator westward, Coriolis will push it to the right in the northern hemisphere, to the left in the southern hemisphere. It's like Moses, he will part the water, which means colder water from below has to come up. As the water is pushed to the west, it begins to pile up against Australia, New Guinea, Philippines and so on. So, it keeps warming it. So, dynamically we are producing cold water here by upwelling and warm water here by pushing it against and building a pile of water and heating it. So that means cold temperatures here, high pressures here, and warm water here, low pressure there. Okay. So if high pressure here, low pressure here, the winds will go from high pressure to low pressure. Where there is warm water, there is going to be heating of the air, and that air will rise and take the water vapor with it, evaporation happening. As it rises, it expands and has up to 5 meters of rain falls on the Western Pacific and the Indonesian seas. That air obviously hits the tropopause, and if we looked at the equator to poles, we had Hadley cell going that way, but we didn't say what happens this way because we had averaged over all longitudes. You can look up the Hadley cell module and the Walker cell module for this, but essentially air is not only going towards the poles, but it is also going towards the east and west. When it hits the tropopause, it will go in every direction. So this part that is going to the east and sinking is called the Walker cell. Sir Gilbert Walker was a mathematician and a physicist who was sent to India by the Queen of England, and he was very avid meteorology buff. So he started looking at famines over India from all the islands, and he found that when pressure over Tahiti and Darwin, which is over Australia, changed their sign, then monsoon would respond and you would get droughts or floods in monsoon. So the oscillation of pressure between Tahiti and Darwin is called Southern Oscillation. Only in the 1960s we realized that El Nino and the Southern Oscillation are the same thing. El Nino, because this water, which is always cold, once in a few years becomes warm when the El Nino comes, and the immigrants from Spain who had colonized these parts saw the warm waters, and it usually comes around Christmas time. Details which we won't go into, but during December, January, February is when maximum warm water comes here when there is an El Nino. So they thought this was a gift from God because warm waters came around Christmas time, brought rains and so on. So they called it as the little child or the Christ child. So El Nino in Spanish means the boy. And once in a while these winds will get much stronger than normal and the waters will get much colder than normal, exactly opposite to the El Nino. And you cannot call it anti-El Nino because so we call it La Nina, the girl child. So El Nino is the Christ child and La Nina is just a regular child. Okay. So as the warm water splashes this way during an El Nino, we don't know exactly why it happens. Theories, and typically when it begins to move, it takes 6 to 9 months, so we can predict it with great confidence in most years, which means we can also predict the impact of El Nino on the monsoon with some confidence and so on. But whatever the reason, when it sloshes this way, the temperatures here become much warmer than normal, which means the warmest waters begin to move, the rising air and the low pressure also begins to move with it. So this becomes drier than normal, this becomes much wetter than normal. In fact, you will get floods and drought, severe mudslides and so on this side, and I will show global figure later on. Whenever you have such a strong heat source, that heat source will affect weather and climate all over the globe. So El Nino affects the entire globe. So during La Nina, all you have to remember is that the winds get weaker, the warm water sloshes this way, the convection moves with it, brings rain on this side, droughts and dust storms and so on this side. We have a longer lecture that you can look up, but I'm putting this in the context of the historical climate change because we will also need it for modern climate change. El Nino has a role to play in the whole business. Okay. So the other thing you have to remember is that if the winds get weaker, the upwelling is reduced, the temperatures get warmer because you are bringing up less cold water. which means the pressure here begins to drop, pressure here begins to increase because it's cooling, which means you begin to reduce this temperature gradient, which means you further reduce the upwelling. So the process starts and there is a positive feedback. Upwelling reduces, winds weaken, which further warms the temperature, which further weakens the wind, which further reduces the upwelling, and so on. And eventually after 9 months the warm water is kind of exhausted and El Nino comes to. Trade winds begin to reappear and cold waters begin to get re-established, and so on. So remember what else we said. When there is cold water here, the atmosphere is putting heat into the ocean. So from one El Nino to the next, the ocean is just collecting this heat. When El Nino comes and it's getting warm everywhere, the atmosphere in fact is not able to put heat, the ocean is putting the heat back into the atmosphere. So it's like a mini global warming. When an El Nino comes, temperatures actually go up. So you have to be very careful, because if you have global warming and you have a lot of El Ninos, then El Nino can accelerate the global warming. So we'll come back and see this bit carefully. So that's basically how the currents are set up. We have the trade winds and the waters are pushed this way, they have to hit the coast and go north and south, and then the westerlies are pushing them back. So you have this kind of what is called subtropical gyre. Subtropics, so tropics are here, these are subtropics, these are mid latitudes, these are the polar regions. So the gyres are circular motions, and upwelling is created basically by those winds. So let's look at a nice animation here. So this is the normal condition. You have cold temperatures, high pressure here, warm temperatures, low pressure here. Winds are blowing from high pressure to low pressure. As you come closer to the equator, Coriolis is weaker. We didn't say that explicitly, but I'm sure you realize on a sphere, Coriolis increases as you go towards the pole. So the warm temperatures warm the air, air rises, takes up the moisture, expands and condenses and rains, hits the tropopause, comes this way, sinks over the cold, and they produce this longitudinal cycle which we called Walker cell. Remember, the Hadley cell is going in the poleward direction. Okay, this is the Walker cell, and you can see that slowly the cold waters begin to the coast and also away from the equator. So you have established what is now called a cold tongue here and a warm pool here, and the Walker cell. What happens during El Nino? So that's the circulation. For whatever reason, as I said, we don't know exactly what starts the process, but whatever reason, these winds begin to become weaker, and winds also begin to appear here in this direction. They begin to push the water this way. These weaker winds begin to reduce the upwelling. So the entire process pushes the warm waters this way, and the convection, rising air, condensation, rain, etc., everything begins to move this way. So by you have much less rain here because you have anomalously sinking air. Remember, every time air sinks, it's drier, clear air, high pressure, no clouds but no rain. Whereas low pressure, convergence, rising air, clouds, rain. So rain has moved to this direction. La Nina is the other one. So you start with the normal condition. For whatever reason, the winds begin to get stronger. More water is pushed to the west and away from the equator. More cold waters are coming up. More water is being piled up here and warmed up. So you will get excess rain on this side, floods and so on. Here conditions. So you can go back and think about your Mayan culture and all the other civilizations from this region that disappeared, and why climates on these coasts are so dry. Basically because you have cold water. Every time you have cold water on the coast, you have to have drier climate on the land nearby, just because there is less humidity, sinking air instead of rising air, and so on. So that is El Nino and La Nina. very short introduction, but come back to why we need to worry about it. So here is a historical record of El Niños since the 1500s. There have been many, as you can see, they occur very frequently, but we will see again and again that there are times when there are more El Niños and there are times when there are fewer El Niños. Just anecdotally I am pointing out, but it turns out that this is true. We will see it again more carefully. So there are definitely decades where there are more El Niños and there are decades where there are fewer El Niños. What does this mean? That means that taking up a lot of heat, and there are decades where the ocean is spitting the heat back into the atmosphere. So you can clearly see this trend in the atmospheric temperature. Okay, so you have to eventually be able to separate the El Nino impact on temperature, greenhouse gases and other impacts. That's one of the more important things to remember. So this is the carbon dioxide now. El Nino also affects carbon dioxide. How? Basically, where upwelling is happening, cold waters are coming up and the carbon dioxide in the water is increasing, which means the pressure difference in carbon dioxide between sea surface and the atmosphere is increasing. So the CO2 will go from the ocean into the atmosphere. How to think about it? If you have a can of Coke or Thumbs Up, it is put under high pressure and cold temperature because it has carbon dioxide dissolved into it, and you keep it cold because cold temperature dissolve more carbon dioxide. So deeper ocean, which is carbon dioxide, near the surface you have warmer temperatures. So in the upwelling you are bringing cold waters to the surface, which means high carbon dioxide water to the surface. That's what increases the so-called partial pressure of carbon dioxide, CO2, in the seawater. Compared to the atmosphere, it's much higher. So this is belching out carbon dioxide all the time. There are regions where the ocean is actually taking up carbon dioxide. This is very important because during an El Nino, if upwelling is reduced, that means this belching out will be reduced. But also with global warming, you can begin to change temperature and begin to change how much carbon dioxide goes into the ocean. This is critical because remember we said ocean takes up 90% of the heat and a lot of the carbon dioxide. If it refuses to take it up, then we are going to begin to accelerate global warming because more and more of the carbon dioxide is going to remain in the air. The warming is going to be faster. So these are the things we have to always as you blow trade winds, you cannot push the water across the equator, not very easy because the water is being pushed to the left in the southern hemisphere, pushed to the right in the northern hemisphere, which means water has to come up because water is moving away from the equator. The same thing happens at the coasts. As you blow winds this way, water is being dragged away from the coast, so colder water has to come up and so on. Upwelling, you will have high chlorophyll. This is a map of chlorophyll measured by what are called ocean color satellites. This is from something called CVIS, Sea Viewing Wide Field of View Sensor. But you can see that coastal regions have high chlorophyll. This region is where the upwelling is happening, also upwelling happening here, and there are different processes by which chlorophyll is produced here. One little trivia for you. Actually, if you look at satellite images of anything like clouds, winds, rain, anything, none of them will show the equator like the chlorophyll does. Remember, the rainfall is maximum in the intertropical convergence zone or the ITCZ, which we will come back and look at. Winds have convergence into the intertropical convergence zone. So everything is on what is called the meteorological equator or the ITCZ or the intertropical convergence zone. Only the chlorophyll shows graphical equator. Just something fun to remember. So how does biology work then? Let's look at the profile of things in the oceans from the surface down to 5,000 feet, 1600 feet, 5,000 meters. And what do you expect? Near the surface, photosynthesis happening. If nutrients are available and there is light, that's where photosynthesis happens, because as you go deeper into the ocean, as you can imagine, it gets darker and darker and there is not enough light. So you expect that the oxygen is going to be high near the surface, because that's where photosynthesis is taking up the carbon dioxide. So carbon dioxide is lower. So this is in this case nutrient. So this means things like nitrate, phosphate and so on, which are essential nutrients for algae to photosynthesize. So nutrients are taken up, so the nutrients are low near the surface. Whatever photosynthesizes falls and dies and reproduces the nutrients, so the nutrients increase. At the same time, oxygen is higher where photosynthesis happens, and those photosynthesized algae are eaten, they fall down and are eaten by all sorts of animals, take up oxygen and breathe CO2 just like us. So there is an oxygen minimum at about 1 kilometer. But then oxygen increases again. The nutrients remain almost same to the depth, which means when there is upwelling, you are bringing up the nutrients, photosynthesis is using it up where there is photosynthesis and where there is upwelling. It is very tricky question if I ask you, why is the oxygen increasing again as we go deeper? This is a good question you can trick your students with if you are a teacher. Remember your thermohaline circulation, deep bottom, and they are filling up the bottom of the ocean. They are sinking from the surface, which means they are equilibrated with the oxygen near the surface, and that high oxygen is sinking, and so the oxygen near the bottom is actually higher than this oxygen minimum where the animals are respiring it. So there is so much information in just these two simple figures, the profiles, and you must emphasize these to the students, because this allows you to combine your atmospheric knowledge, ocean currents, Ekman divergence or upwelling, Coriolis, thermohaline circulation, biology and so on, right. So these simple figures teach us all these things. So we will continue with the carbon dioxide profile and look at how different oceans are different because of the thermohaline circulation, because they all begin to be a critical part of global warming, and how global warming is going to affect the upwelling, primary production or photosynthesis, marine food web, where things live, who can continue to live, who will get affected by global warming and so on. So this is why we will continue to introduce these processes along the way, but you have to find a way to course and teach everything at the right time. This is the way I am doing it as I come to those particular processes, but you can choose how you do it. See you next time.